This video lecture here contains a brush up on some of the fundamental mathematical concepts that we are going to use in the course on molecular modeling. Before we begin, a few definitions is in place here. When we talk about a scalar, what we mean here is a single number. When we talk about a vector, what we mean is a single set of numbers, and the vector here is characterized by its length and direction. And when we talk about a matrix, what we mean is a two-dimensional array of numbers. An example here, consider a collection of n particles represented by 3n coordinates, that is the x, y, and z coordinate for each of the particle. Then the energy of the system, E, is a scalar. The gradient is a vector with 3n elements, and these elements here consist of the partial derivative of the energy with respect to a given coordinate. If, for example, this first term here is negative, then it means that if we move this particle here, characterized by this coordinate, if we move this particle along the positive x1 direction, then the energy will decrease. A Hessian, this is a 3 times 3 matrix, and the elements are defined as the second derivative of the energy with respect to two particle positions. We will later on get back to working with examples involving Hessians. A problem that we meet many times in the sciences is that of matrix diagonalization, that is, how we can actually transform a matrix into a diagonal form, that is, a matrix containing only non-zero entries on the diagonal. One way of obtaining the matrix in its diagonal form goes by the route of calculating the so-called eigenvalues. When we calculate the eigenvalues of a matrix A, then what we do here is that first we take A, then we subtract along the diagonal the quantity lambda here, and then we take the determinant to the resulting matrix and put this equal to 0. Now, by expansion of this determinant here, this will give us an equation, a polynomial equation in lambda of order n, where n is the same number as the original dimension of this matrix. So in order to be able to determine the eigenvalues of a matrix and thereby to determine the matrix in the diagonal representation, it becomes essential to be able to calculate the determinant of a matrix. For a 2 by 2 matrix, we use here, we could call it the definition of a determinant, namely that it is A11, A22, minus A12, and A21. For a 3 by 3 matrix, what we can do is that we can expand the determinant along a given row or a given column of the original matrix. So what we do here is that we expand this determinant here along the row number 1. It will give us then A11, and then we remove here from the original determinant both the row and the column that contains A11. So back we have A22, A33, A23, and A32. Then we take the next element in the column, A21, and we remove again the row and the column containing A21, and we have back A12, A13, A32, and A33. For the last element, A31 here, we again remove the column and we remove the row, and we have back A12, A13, A22, and A23. Now for the sign of these three contributions here we use the rule that if we add the two indices here, A11 in this case, 1 plus 1 is 2, and if this equals an even number, then the sign is plus. If it equals an odd number, then the sign is minus. So in this case here, we have A21, 2 plus 1 is 3, so this is odd, meaning that we should have a minus here. 3 plus 1 is 4, so it is even, meaning that we should have a plus sign in front here. So this is the way that we can calculate determinants of the matrices. One place in chemistry where we use this concept of determinants a lot is, for example, when we consider Hügel theory. In Hügel theory, we construct a Hügel Hamiltonian here based on the Coulomb and resonance integrals, and then what we do is that we find the eigenvalues of this Hügel Hamiltonian here, and we can do an interpretation of these eigenvalues in terms of the orbital energies. And we will get back to such an example here in the exercises later on. Shifting the focus a bit here, another concept that we will be using a lot in this course here is functions of several variables. If we have a function, for example, the ideal gas equation, then this contains more than one variable. For example, if we want to calculate here the volume of the gas, then it is a function of three variables, P, T, and N, given by nRT divided by T. So for such a function of several variables, we can calculate what we call the partial derivatives by differentiation with respect to one variable and keeping all other variables fixed. So for example, if we have the function z here equal to x squared minus 2xy minus 3y squared, then we can calculate the partial derivative of the function with respect to x. This will give us from this term here 2x, from this term here it will give us 2y, and this term here will not contribute because this is a constant with respect to x. The partial derivative with respect to y, here the first term x squared here will be 0 because this is a constant with respect to y. The next term will give us minus 2x, and the last term will give us minus 6y. This concept here of partial derivatives become essential when we are to characterize a given function in terms of stationary points. So in 2 dimensions, the requirements here for having a stationary point is that the partial derivative of the function with respect to x and with respect to y should be 0 at the same time. If this is the case, then we have at the point x point y here a stationary point. In addition, if the second partial derivative of the function with respect to x, indicated here by fxx, is less than 0, and if the second derivative of the function with respect to y both are less than 0, then we have a maximum. If they both are greater than 0, then we have a minimum. If the following condition here is fulfilled, that is, if the product between the second derivative with respect to x, the second derivative with respect to y, minus the squared of the mixed second derivative is greater than 0. So these rules here is a generalization of the rules that we have for a function of one variable and can be used to classify a function in terms of both stationary points and also the nature of these stationary points. And this becomes essential for us when we later on will consider potential energy surfaces that we need to classify with respect to minima and to maxima. Another concept that we will meet frequently in this course here is operators. An operator is defined by its action on a function, and when an operator works on a function, it produces another function. As an example, we can consider the following function here, and we can consider the gradient or the differential operator called nabla. When this operator here works on the function, what it does is that it performs a partial derivative with respect to x, y, and z of the function, meaning that it produces now a new function. Now the last concept that we will touch upon in this brush up here is that of how we can represent a complicated function in terms of a set of simpler functions. And one way of doing this is through the use of the Taylor expansion. Now the figure here shows the Morse potential as a solid line, and you have seen already in video lecture 1 the Morse potential which we used in order to describe the stretching motion of a bond in a given molecule. What we can do here now is that we can perform a Taylor expansion of this Morse potential here around the point x equal to 1. And you can see that as we go higher up in order of this Taylor expansion, the polynomial order, that is a Taylor expansion to second order, a Taylor expansion to order 3, a Taylor expansion to order 4, that we get an increasingly better agreement between our approximating function and the true function. So the Taylor expansion is defined by the equation up here. So what we do is that we take our original complicated function and then we represent this in a set of polynomials by saying that at the expansion point we require that the two functions have the same point. Then we add the derivative of the complicated function with respect to x evaluated at x0 times x minus x0. This would be a Taylor expansion to the first order. We can also add another term here, the second derivative of x with respect to x also evaluated at x0 times x minus x0 to the power of 2. This would now represent a Taylor expansion to order 2 and so on. And as we go higher and higher up in order of this Taylor expansion here, we expect to have a better and better representation of the true function. Note here that per definition the Taylor expansion works in the way that at the expansion point, in our case here x equals to 1, the two functions, the original function and the approximating functions, have exactly the same value. Another way of representing a complicated function in terms of a set of simpler functions is through the use of a basis set expansion. And you have already seen examples of this in your introductory course on quantum chemistry, namely where you investigated the LCAU, or the linear combination of atomic orbital concept. What you did back then was to take a molecular orbital, which is considered as being a complicated function, and then you represented this as a linear combination of atomical orbitals, which are considered to be more simple functions. So in general terms, what we do is that we take our complicated function here, and then we write this as a linear combination here in terms of a set of simpler functions, also called the basis functions. We can then apply different procedures in order to determine the amount of the different basis functions that should enter into the expansion, that is, to determine the value of the c's here. For example, in the case of the linear combination of atomical orbitals, here we used an energy criteria, meaning that we were seeking the solution which gave us the lowest energy. These two examples here also contains an illustration again of the Morse potential, now represented in terms of a basis set expansion. The functions that we use as our basis functions here is a polynomial to the second degree, to the third degree, and to the fourth degree. And again, you can see here that as we go up in order, we get a better agreement between the original function, the Morse potential, and the approximating functions. And you can see here that this better agreement in the terms of the basis set expansion, well, we get this better agreement now for a range of x values. In the case here, we have a fairly good agreement for x values between 0.1 and up to 2.1. So it means here that in the basis set expansion, what we seek is to obtain a good representation of our original function for a range of values for our variable, in this case here x. If we just go back here to the Taylor expansion, then this is a bit different, and this is what differentiates these two methods of function expansion, namely that in the Taylor expansion here, what we get per definition is a function that exactly equals the original function in a given point, and then approximates the original function in a range of points that are lying close to the expansion point. On the other hand, in the basis set approximation, what we do here is that we obtain an approximating function which resembles the original function in a range of x values in the best possible way.